So far we've been applying integrals to motion in physics, one-dimensional motion, back and forth, either left, right and left, or up and down. Let's apply integrals now to two-dimensional motion, where you're not along some straight line, but maybe on some curve on the plane, like a bug walking around on some curve, or maybe even some three-dimensional motion through space. So we'll start fairly simple, and then we'll use technology ultimately to deal with more complicated examples. So let's consider this system of parametric equations. X equals t and y equals t to the 3/2 power. That's a system of parametric equations. It's common to call the first function, say, f of t, and the second function g of t. So I will do that. This will be f of t, and this will be g of t. We can quickly use our calculator, for example, to graph this and see it as a motion if we like. This could describe the motion of a bug across the page. Let's go ahead and go to parametric mode in the calculator. So I'm going to press the mode button, go down and change it from function mode to parametric mode like that. And then again, when you go to your y equals screen, it looks different than usual. You see a spot for two functions of t instead of one function of x. And for our example, x will equal t. I press the variable button and it is a t instead of an x. And then go down, tab down to the y. Y is going to be t to the 3.5 power, which is the same as 1.5 power, or 3/2 power, I meant to say, which is the same as 1.5 power. And let's think about what happens with this motion as t goes between, say, 0 and 4. So 0 is less than or equal to t is less than or equal to 4. I'll go ahead and graph it. Before we graph it, let's just think about it a little bit. As t increases here, both x and y are going to increase. And in fact, when t is 0, the bug is at the origin, right? Because you'd get 0, 0. It's got to be moving up and to the right as t increases. T to the 3/2 ultimately increases faster than t does, so y is ultimately going to increase faster than x does. Maybe not at first, but ultimately, let's go ahead and graph it. Let t go from 0 to 4. I'll keep the t step at 0.01. What kind of window should I use? Well, x equals t, so x could go from 0 to 4. Y equals t to the 3/2. What's 4 to the 3/2 power? It's 8. Because it's the square root of 4, which is 2 cubed. 2 cubed is 8. So this is going to be a window that'll be fairly nice for seeing the motion here. I'm about to graph it. You'll see a graph get traced out. Think of it as a motion, not just a graph. It's a bug walking across my calculator. Ready? 1, 2, 3, go. Kind of slowly, but there it goes. And yeah, ultimately, y is growing faster than x does. Kind of looks like a parabola, but it's not technically a parabola. It has kind of a half a parabolic shape, though, to it. What might we be interested in knowing about here? Well, one thing we'd be interested in knowing about is thinking about vectors. Position vector, velocity vector, maybe even an acceleration vector. We also might want to know the speed of the bug and whether it's a constant speed or not. And we might want to know the distance traveled. Now, you can actually approximate the distance traveled just looking at the figure here. We're starting at the origin, 0, 0, and ending at the point with coordinates 4, 8. If the bug traveled on a straight line from 0 to 0 to 4, 8, the distance traveled could be found from the Pythagorean theorem. You're in your head, square root of 4 squared plus 8 squared. 8 squared, 64, 4 squared, 16. 16 plus 64 is 80. Square root of 80, about 9, would be the length of the line segment between these 2 points. The bug actually traveled along a curve, so the answer is going to be a bit bigger, but probably not a ton bigger. 9 something might be the distance traveled. Let's see if we can figure these things out. So the position vector, I will figure that out right now. I will also program these things into Mathematica so we can visualize them. The position vector is commonly called R of t. And remember, this little half arrow notation above the letter emphasizes this is a vector. You could use a full arrow if you wanted to. Some people even put the arrows below the letter. In books, vectors are often boldface. And there's lots of different notations you could use for the vector. You could do f of t times I hat plus g of t times j hat, where remember I hat and j hat are called the standard unit vectors. I hat points directly to the right and has a length of 1 in whatever measurement units you're using, say centimeters. And j hat points directly upward and has a unit length of 1. I could do that. I'm not going to bother. I'm going to use the notation that I prefer when I teach multivariable calculus, and I think Jed Yang uses this notation as well. Pointy brackets, f of t comma g of t, inside pointy brackets. There's actually some other classes like linear algebra and differential equations where we prefer writing vectors as column vectors, because maybe you've learned about matrix multiplication. If you take a matrix times a vector, you want it to be a column vector. I'm mentioning those things just so you're aware of them, just so you're not thrown off when you encounter them in the future. But this is good enough for us right now. It's not a constant vector. It depends on t. This vector, this arrow that I end up drawing from this, will not have a constant length, and it will not always point in the same direction. If I put its base, its starting point at the origin, its tip, the tip of the arrow will always be at the location of the bug as it moves. That's what I'm going to try to animate. The velocity vector v of t is the derivative of the position vector. And how do you find the derivative of a vector? You differentiate each of its so-called components or components. I like saying components. Or coordinates. There's really 3 words that's, well, 2 words, one pronounced 2 different ways, representing these things in the vector, the f of t and g of t. You get a new vector whose components are f prime of t, comma g prime of t. In this example, the first component of that is constant 1, but the second component is still a function of t, 3/2 t to the 1/2. And if I like it, I can also find an acceleration vector, a of t, which is the derivative of the velocity vector, same as the second derivative of the position vector, having components f double prime of t, comma g double prime of t. And the first component in this example is going to be 0, right? The derivative of 1 is 0. And the second component, I differentiate this, I'll get 3/4 t to the negative 1/2. Okay, great. Let's visualize these things now. You're not going to have to know how to do this for the test, but in the long run, this is really a good thing for you to use Mathematica in the future, not just in math classes, but maybe in physics classes, to help you understand what's going on. But you got to know how to do it. I will go ahead and define my functions. F of t is t, g of t is t to the 3/2. Those are scalar valued functions. The outputs are real numbers. R of t is a vector valued function. The output is a vector, which in Mathematica, you don't want to use parentheses. You don't want to use pointy brackets. You want to use curly braces. It's just the way Mathematica does things. But I'm putting f of t and g of t into the components of that, so to speak. Then I can define the velocity vector to be the derivative of the position vector like that, and the acceleration vector to be the derivative of the velocity vector. There's a bunch of calculations I can do. And then, for example, I can see that Mathematica got the same answer as me for the acceleration vector. 0 for the first component, 3/4 t to the negative 1/2 for the second, which is the same as 3/4 times square root of t. More importantly, though, is visualizing this. I'm going to type the code as fast as I can. Don't worry about details. There's a lot of details that I like to add to this code to make it look as pretty as possible and type as fast as possible. I'm going to be making an animation, so I use manipulate. Makes animations. I've got an animation parameter that I usually call B that starts just barely bigger than 0. And in this case, it goes up to 4. B is going to be the ending time of the motion, but it's going to change so that I see an animation. I'm going to show a couple different graphs together, one of which is going to be a parametric plot of the curve itself, which is really R of t. When I use parametric plot and put R of t in there, essentially Mathematica is treating that as a curve that gets traced out, not a vector. T goes from 0 to B. I'd like to probably make this nice and easy to see. Thickness 0.01 I like using, and then say blue. I'm probably going to also want to fix the plot range to be like we did with the calculator, 0 to 4 in the horizontal direction, 0 to 8 in the vertical direction. This will make a graph as it stands. I have a tall, skinny graph. Maybe I should change the aspect ratio. Yeah, I probably should. Let me change the aspect ratio to make it not so tall and skinny. That'll be better. The axes are no longer to scale. I mean, they weren't to scale to begin with, I don't think, but. So there's the motion. A little herky-jerky. I'd like it to be smoother, but oh well. I can add more code in here inside the show, but after the parametric plot, right here, put another comma, add graphics. What is graphics going to do? It's going to allow me to put some vectors in the picture, as well as maybe a point at the location of the bug. Maybe this black point that I'm about to make is going to be the bug itself. You can do it right now. There's the bug, black dot on the page. Make it a bigger bug. Let's put this with 3 instead. Now it's a bigger bug. Move along the screen. Add in some vectors now. Again, don't worry about this syntax. I've just done this syntax so much in my life that I can do it pretty quickly. I always forget what arrowhead should be, how big the number I should put in arrows. I'll try 0.05. Arrow means it makes an arrow, a vector. So now I've got the position vector in there. Not very thick, though. I think I want it thicker than that. Maybe I'll make the curve a little less thick. And the arrow a little thicker. Oh, that's too thick. Okay, not quite so thick for the arrow. Maybe a bit bigger with my arrowheads. I'm trying to get the ideal picture in my own mind. That's pretty good. Okay, so the arrow is like, it's almost like it's a blue pen tracing out that blue curve. It's always pointing from the origin to the bug as it moves. That's called a position vector. Again, vectors are arrows. They have lengths and directions. You can work with them symbolically with the components. If you take mechanics, for example, a more advanced physics class, you're going to want to think about this kind of thing all the time in that class. And maybe even other physics classes could be useful too. I'd like to put the velocity and acceleration vectors in here too. I'm going to make the velocity vector red. Turns out, though, with the velocity vector, it's not best to put the starting point of the arrow at the origin. It's better to put it at the location of the bug. I think I want my black point size point to be in a different spot here actually as well. Just to make this as nice as possible. You want to put the velocity vector to start at the location of the bug as it moves. And without explaining why, this code should do that. So that red arrow is a velocity vector. But it changes. It changes as the bug moves. But notice, excuse me, It's always tangent to the curve if you put its starting point at the location of the bug. It's always pointing in the direction of motion. That's a nice property of velocity vectors. That's partially why we call them velocity vectors. More than that, it's tough to tell, but it is getting a little longer as it goes. It's getting slowly longer. The acceleration is non-zero. That velocity vector is getting longer, meaning the speed is getting higher. The speed is the length of the velocity vector. I mean, there's a formula for the speed, yes, but I haven't written it down yet. Let's put the acceleration vector in the picture as well. I'll make that magenta. Why don't I think of that when I say blue? But I do think of it when I say magenta. Whoa, the acceleration vector is pointing straight up, it looks like, and it must be really long. It's off the screen. Now it gets short, though. It is pointing straight up all the time. It's really long at the start, and then quickly gets shorter, but it does look like it always points straight up all the time. That should make sense. The first component, the horizontal component of the acceleration, is always zero, no matter what t is. And the second component is this, which again is the same as 3/4 square root of t. And if t is close to zero, that goes to infinity as t approaches zero from the right. At time zero, technically the acceleration vector does not exist. The acceleration is effectively infinite for this motion at time zero, but I am at a slightly positive time here, but the acceleration vector is really long. Wow, really long. You let b increase even slightly, though, then it gets pretty rapidly shorter. But it's always in the upward direction. Somehow, I'm not explaining how, the velocity vector, the red arrow, measures the rate of change of the blue arrow. It's the derivative of the blue. And the acceleration vector, this pinkish magenta arrow, somehow measures the rate of change of the red arrow. Acceleration is the derivative of velocity. I'm not going to explain how, but eventually, like in multivariable calculus, you should try to make sure you understand why they measure rates of change, those vectors, geometrically. What I'm more interested in here for a Calc 1 class, near the end of the semester when we're talking about integrals, is I'm more interested ultimately in the speed and integrating the speed to find the distance traveled. That idea, integral of the speed as the distance traveled, still works, even though the motion is two-dimensional. But what is the speed? The speed, well, first of all, it's a function of t. I didn't write this before, but it is a function of t. It could be a constant function of t, and then I wouldn't maybe have to write the of t in there. Essentially, it's the length of the velocity vector. Length of v of t. Being a length, it's not a vector. The speed is not a vector. The velocity is a vector. The speed is not a vector. Essentially, by the Pythagorean theorem, it's the square root of the sum of the squares of the components of the velocity vector. Square root of f prime of t quantity squared plus g prime of t quantity squared. For this example, that becomes the square root of, look at these expressions, 1 squared plus 3/2 t to the 1/2 squared, which is the square root of 1 plus 9/4 t. That's a function that represents the speed of the bug at any moment in time. What does its graph look like? What I'm about to draw is an ordinary kind of graph. T is the horizontal axis. Say speed is the vertical axis. This is not the parametric curve. The parametric curve is really drawn in an XY plane. right? Remember that? You draw XY plane, and then X and Y depend on T, the bug walks around over time. Time in the parametric curve that you draw by hand is just in your imagination. With a calculator or with Mathematica, when I use manipulate, I can actually see the curve be traced out as time goes by. Anyway, if you plot this curve, when T is positive, it looks about like this. It looks kind of like a square root graph. Its value at T equals 0 would be square root of 1, which is 1. And it doesn't matter that the motion is in a two-dimensional plane going along a curve. That doesn't matter. The distance traveled is still the integral of the speed. The total distance traveled is still the integral of the speed over the interval that T is varying over, which is 0 to 4. Can this integral be done? Could you do it? Yes, but it is a little tricky. I'm about to use the fundamental theorem of calculus. To try to do that integral there. But it's tricky because this integrand function, this speed function, well, what's an antiderivative of it? It's not so clear. There is a method that you'll learn in Calc 2 called substitution. Sometimes it's called U substitution. Our calculus book calls it W substitution. Another kids program thing. When you do a W substitution, you end up finding DW. Hey, Arthur. Okay, but when you use U, then you end up finding DU, and well, that doesn't have any kids program come to mind because of that. I need an antiderivative of this. Again, it's not so clear. I don't know. Well, no, I think you could figure it out given enough time. It's got to still involve 1 plus 9/4 times T, and it would have to be to the 3/2 power, right? Because if you had something like this, 1 plus 9/4 T to the 3/2 power, leave a little space there. The derivative of that, you'd bring the 3/2 down and get a 1/2 power, right? 3/2 minus 1 is 1/2. But then the chain rule would give you an extra factor of 9/4, which we do not have there. You also have to compensate instead, because you added one, when you differentiate power functions, like say x to the 5th power, you bring the power down in front, 5, x to the 4th power, you subtract 1 from the exponent. When you do integration, you do it in reverse. You add 1 to the exponent, and instead of multiplying by the power, you divide by it. I got to divide this by 3/2. And also to compensate for the chain rule in multiplying by 9/4 when I differentiate this, I need to multiply by 4/9 out front. Tricky, tricky, tricky. If you don't believe it, if you're unsure, you can always check it. Before we check it, let's simplify it a little bit. Dividing by 3/2 is the same as multiplying by 2/3. Right? Divide by the fraction 3/2 is the same as multiplying by its reciprocal 2/3. 4/9 times 2/3 is 8/27. Yeah, let's imagine differentiating this in our minds. We bring that 3/2 down. Just forgot my T in there. We bring that 3/2 down, we get 8/27 times 3/2. That's 4/9. 8/27 times 3/2. 8/27 times 3/2. The 3 cancels with the 27 to leave a 9. This 2 cancels with the 8 to leave a 4. It's 4/9. But then you subtract 1 from the exponent to get 1/2 like you should. Then because of the chain rule, you multiply by 9/4. Hey, and 9/4 times 4/9 is 1. This works. This is right. This is an antiderivative of that. Again, in Calc 2, you'll learn to be a little bit more careful about it, systematic about it, and use substitution. But I'm not doing that. That's applying the fundamental theorem of calculus. All that's left to do is to simplify it. Plug in 4 for in place of t. 9 fourths times 4 is 9. And then subtract what you get when you replace t with 0, which is not 0 here. It's 1 plus 0 to the 3 halves, which is non-zero. It's 1. This is a 1 here. The answer is not a nice number. It's 8/27. 10 to the 3 halves is, well, 10 to the 3 halves, which is the same as 10 times square root of 10, minus 8/27 times 1. It's not a nice number, but it is what it is. I could write it as one fraction if I like. 80 square root of 10 minus 8/27 is the distance traveled. Now remember what the answer should be. It should be, when you approximate, a little bit bigger than 9 perhaps. Let's see if that happens here. 80 times square root of 10 minus 8 divided by 27 is, yes, a little bit bigger than 9. 9.07 centimeters second. That's the distance traveled. Here's something kind of subtle that I'm about to say, but really important, especially for Calc 2. What if I'd used a different upper limit of integration there? Like 3 instead of 4, or 5, or 2.2? I'd get a different answer, wouldn't I? I'd get a different distance traveled. It's still the same motion, but the time interval we're thinking about is different. So I'd get a different answer. So what I'm trying to say here is that if I allow the upper limit of the integral to vary, to be a variable, I'm really going to get a function. This is pretty important. Maybe I call a general upper limit b and define a function capital F of b to be the integral from 0 to b of the speed. So the variable for this function is b. T for the integral, well, yes, it's time, but it really doesn't matter what I call it. I'd still do the same calculation in the end. And with the speed still being 1 plus 9/4 t to the 1/2 power, I could still use the fundamental theorem of calculus to say this is, just copying what I wrote down before, 8/27 1 plus 9/4 t to the 3/2 power evaluated from 0 to b. And I could simplify this even though I don't know what b is. And I get 8/27 1 plus 9/4 b to the 3/2 minus 8/27 times 1, right? Times 1, because when you plug in t equals 0, you get 1, and 1 to the 3/2 power is 1, and 1 times 8/27 is 8/27. That's a function of b that gives you the distance traveled no matter what b is. And if b is 4, we get the answer that we had on the previous piece of paper. That was about 9.07. Being a function of b, I guess I could graph it. I guess I could differentiate it. What would happen if I differentiate this? Capital F prime of b Bring the 3/2 down, get 4/9. Don't forget about the chain rule. Multiply by 9/4. This should feel familiar. -0. Right? The 4/9 and the 9/4, that should feel familiar. Yeah, they completely cancel. You're left with 1 plus 9/4 b to the 1/2, which is the same as the speed at time b. How about that? F of b really is a distance traveled function. I could call it dist of b. And then you can take a step back and say, well, why bother calling it b? Why not call it t? And I could do that. And get a distance traveled function of t that would be this formula, except use a t instead of a b. This is illustrating that when you make the upper limit of your integral a variable, you can define a new function that's an antiderivative of the original. That's sort of a twist on the fundamental theorem of calculus. But the fundamental theorem of calculus, I've been saying that if you want to integrate, I'll use x now instead of t as my variable. If you want to integrate a function f of x over an interval from a to b, find an antiderivative capital F and do this, where capital F prime of x equals little f of x for all x in the interval from a to b. That equation tells you how to figure out integrals. If you know, or if you can figure out capital F, an antiderivative, just do that. We've been doing that a lot. What I've just done here sort of illustrates a related concept. If you define a function by making your variable, your upper limit a variable, that function, in fact, must be a function whose derivative is the integrand. Symbolically, in the general case, we could write it like this. The derivative with respect to x of an integral where the variable for this function is the upper limit of integration of some function little f, I'm not going to specify its variable yet, is essentially that function little f. What should I call the variable in here? I'll call it anything you want, except don't use letters you've already used. Don't use a D. Don't use an A. Don't even use an X. Use something else. Oh, I don't know. How about U? But over here, I want the variable name to match what I'm differentiating with respect to. I want this to be an X. In the problem we just did, the B is like the X and the T is like the U. The B is like the X and the T is like the U. But in the end, you got the derivative to be something involving B. Just like here, the derivative of this has to involve X, because that's the variable I'm differentiating this. This thing that's the integral, where the upper limit is a variable, is a function of X, not U, not A function of X. This formula right here is section 5.3 in our textbook. This formula right here is actually in chapter 6. It's section 6.4. You'll see it again in Calc 2. I'm not going to stop talking about this. I will still talk about it here a little bit in Calc 1. These are, in a sense, both forms of the fundamental theorem of calculus. See, this one's used more often by most people, because most people just want to evaluate integrals. But to know that the integral defines an antiderivative is important in some applications too. This one applies even when you can't figure out what the integral is as well. Here in this example, we did figure out what the integral equals, so we were able to differentiate it. But this one works even when you can't figure out the integral. That's kind of mind-blowing. And it's useful sometimes, even when you can't figure out the integral. I will show you an example here today. We could go to Mathematica now. We could also graph things here. Let's also type in the speed function. Speed of t is the square root of f prime of t squared plus g prime of t squared. And we can confirm its formula is what I showed you by hand. Square root of 1 plus 9 force t. We can get the distance traveled function here in a couple different ways. We could just integrate this thing with an indefinite integral. Like that. And then choose a plus c to make the value of this function 0 when t is 0. Why would I want to do that? This is supposed to be essentially the distance traveled as a function of t, but it's not quite, doesn't quite work. Think about what we got by hand. We got by hand essentially that thing, but then minus 8/27. You have to subtract the 8/27 so that the distance traveled at time 0 is 0. Plug in b equals 0 here, you'll get 1 to the 3 halves. You ultimately get 8/27 minus 8/27, 0. This function that Mathematica computes with the indefinite integral symbol does not equal 0 when t is 0. It equals 8/27. So to get the true distance traveled function, I need to take that and subtract 8/27 from it. That'll now have the property that at time 0, you've gone 0 distance. Now I can plot these things, plot both the distance traveled and the speed as functions of t. I'll make the distance traveled blue and the speed red. And there they are. The red graph, that was the one I drew by hand, the square root of 1 plus 9 force t. That's the speed. The blue one is the distance traveled. It's the integral of the red. The red one is the derivative of the blue. Think about the slope of the blue. It's always positive, so the red always has a positive output. It's a minimum slope at t equals 0, so the red has a minimum value there. The graph of the blue is concave up. Its slope keeps getting bigger, just like the speed keeps getting bigger. The derivative, the speed, keeps getting bigger because the blue graph has a bigger and bigger slope over time. And you can also think about areas. At any value of t, like t equals 2, for example, the output of the blue graph is the area under the red graph. Don't forget about the area interpretation. For example, at t equals 2, you can see, well, we can even figure it out. What's the distance traveled at time 2? It's about 3.5. That's the second coordinate of this point right there on the blue graph, about 3.5. That's the same as the area under the red graph between 0 and 2. If I shade an area under the red graph between 0 and 2, its area is going to be about 3.5. You could take time to think about that, see if it makes sense. I mean, the area of this rectangle that I'm tracing with the cursor here, watch it. That's a rectangle with base of 2 and height of 2, area of 4. The area under the red graph is smaller than that. Yes, it's about 3.5. You notice lots of ideas going on here. Try to keep reinforcing the same things, including on Friday, including next Monday before we review for the exam. You got to work on the homework problems. You got to think about this stuff over and over again. It's easy to just forget, right? Oh, I kind of understand it right now. Then you come back 2 minutes later. Oh, I've completely forgotten, right? You got to think about it consistently. If it's going to stick in your brain, make it stick. For a little bit of fun, let's do a more interesting example. And then we'll wrap up class by talking about other applications. What's a more interesting example? How about if we change, let me also do the speed formula here. What I'm going to do is I'm going to change f of t and g of t. Okay, well, this example is going to be fairly simple. I'm going to make f of t equal cosine of t and g of t be sine of t. Hope you remember maybe from one of the extra problem solving videos that I made about parametric equations that when you use cosine and sine here, you get a circle. I don't know why the t's are red there. Let's just see what happens. Okay, I don't know why those are red. Makes me think something's wrong, but it seems to be working. Yeah, and what is a of t? That's right. The speed is the square root of cos squared plus sine squared. Mathematica didn't simplify to get that. You know that's 1, always, for all t. This is uniform circular motion at a constant speed. If I graph what's going on here, come on. Oh, put the origin in the right spot. Axes, origin. And get rid of that aspect ratio. This is uniform circular motion at a constant speed. The blue arrow is still the position vector pointing from the origin to the location of the bug. Let's let time go to 2 pi instead of 4. That blue arrow, which is underneath the magenta arrow, is the position vector. It's always pointing from the origin to the location of the bug as it moves. The red arrow is the velocity vector. It's always tangent to the circle. In fact, it's always the same length. The velocity is not constant, but the speed is. The velocity is a constant length, but the direction of the arrow changes. So it's not a constant vector if its direction changes. And it's got a rate of change. The magenta colored arrow pointing straight at the origin is the acceleration. Pointing straight toward the origin. You know that happens with uniform circular motion. I could make the motion non-uniform, though. I could do another example where I replace t with, for example, t squared. Still do the speed. I no longer get a constant speed. It's that, which turns out not constant. And if I make an animation of the motion, you will see, well, the red arrow evidently is really tiny at first. The velocity is 0, though the acceleration is large. But the velocity does get longer and longer as time goes by, and I shouldn't go so far. Let's go to square root of 2 pi instead of 2 pi. Still moving along a circle. The blue arrow still points to a circle. The red arrow, the velocity vector, is always tangent still, but it keeps getting longer and longer. You're speeding up. The acceleration is the rate of change of the velocity. It keeps getting longer and longer as well. The speed function can still be integrated, and we can still find the distance traveled function. There's the integral of the speed. It does have a value of 0 when t is 0, so in fact, it is the distance traveled function. And when t is positive, square root of t squared is t. So the distance traveled function is actually t squared here. And you could plot that. One more real quick, really interesting example. What if I make the inputs for the cosine and sine different? Like this one 3t and this one 5t. And I'm going to let t vary from 0 to 2 pi over 5. What do I have? Is it circular motion? If I make the inputs to the cosine and sine different? No, it's not circular motion any longer. It is what's called, oh, that looks like circular motion. Did I not enter that? I didn't enter this. Okay, there we go. Now it's better. It's non-circular motion. I want to go past 2 pi over 5. Why is it not going far enough? Try 2 pi over 3. It's non-circular motion, but it sure is a pretty motion. It's called the Lissajous figure. Evidently 2 pi over 3 is still not good enough. Okay, 2 pi. The entire curve is a very pretty picture. There it is. It's like you're on a parking lot going around and around in different ways. These ideas still work, and the distance traveled is still an integral of the speed as long as its value at 0 is 0. And Mathematica, what is that integral? It's thinking, and it's going to give up. Why? Because the integral is really hard to do symbolically. Usually it gives up by now. Okay, it stopped. It's trying to integrate this function, which is not a constant function. It's a very complicated function. Evidently, it doesn't have a simple answer. There is an answer, it's just not a simple formula. But the ideas still apply. But what do you have to do if you wanted to figure out the distance traveled? You have to do something called numerical integration. You have to use Riemann sums, like the left and right Riemann sums, and average them. You would have to. Fundamental theorem of calculus is still true, it's just not useful.